This is Fundamental Problem 1 from Chapter 13, our first example problem from this chapter. The motor winds in the cable with a constant acceleration such that the 20 kilogram crate moves a distance of 6 meters in 3 seconds starting from rest. So the initial velocity is 0, and let's say the initial position is 0 also, such so that when time is equal to 3 seconds, the position is equal to 6 meters. We want to determine the tension developed in the cable. The coefficient of kinetic friction between the crate and the plane is 0.3. So we're going to start off by drawing a free body diagram. And we know we have the force of gravity acting straight downwards on the object. So I have the force of gravity acting downwards. And I have a normal force, which is called the normal force because it acts perpendicular to the surface. So there's my normal force. And I was given a coefficient of friction. So I know I have friction, and that points in the opposite direction of the motion of the crate. So that's directed down the incline. And the crate is moving up the incline because of the tension in the cable. So I want to draw a new free body diagram now, and I want to break the force of gravity up into components. So I have my normal force here, I have my tension here, I have my force of kinetic friction, and for the force of gravity, to break it up into components, I'm going to need to know either, hang on a minute, the force of gravity is pointed straight downwards like this. I know this angle here is 30 degrees. I want to use a tilted coordinate system, so this is the y direction and this is the x direction. If this angle here is 30 degrees, this angle here would be 90 minus 30 degrees. So this angle here, because this is a 30-degree angle, this angle here would be 30 degrees. So when I break this up into components, this component is, the cosine component. And then I have another component pointed down the incline in the negative x direction, and that is the sine component. Okay, so if this is the x direction and this is the y direction, now I can take Newton's second law for x and y components and go from there. So the crate has a constant acceleration. That acceleration is in the x direction, so the crate is not accelerating in the y direction. The crate is not even moving in the y direction. If it was moving in the y direction, it would either have to be coming off the surface or sinking into the surface, but it's not. So it's moving just in the x direction. So the acceleration in the y direction is equal to 0. And let's say instead of the force of gravity, let's just replace that with m times g. So I have mg sine of 30 degrees, and this is mg cosine of 30 degrees. Okay, so when I sum up the forces pointing in the positive y direction are positive, forces pointing in the negative y direction are negative. So I can say the normal force minus mg cosine 30 degrees is equal to the mass times the acceleration, which is 0. Or if the acceleration is 0, I could just say the forces pointing in the positive, the sum of the forces pointing in the positive y direction is equal to the sum of the forces pointing in the negative y direction, which I could get from rearranging this equation also, and I have the normal force is equal to mg cosine of 30 degrees. So let's move on now and look in the x direction, but we may want to come back to that later. So looking in the x direction, I have the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction, and I know the acceleration in the x direction is constant. In the x direction, I have tension pointing in the positive x direction. I have the force of kinetic friction pointing in the negative x direction, so I put a negative sign there, and also the force of the x component of the force of gravity, which is mg sine of 30 degrees. and that's equal to the mass times the acceleration in the x direction. I know the mass, I know little g, I'm looking for the tension, I don't know the acceleration. I do know that it's constant. And I can find the force of kinetic friction because I know the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. And from looking at the forces in the y direction, I found that the normal force was equal to the mass times g times cosine of 30 degrees. So the mass is 20 kilograms, and g is 9.81 meters per second squared in SI units. And so I get 169.9, and the units are kilograms times meters per second squared, which is equal to a Newton, and those are the units for force in SI units. Do be careful because this is the normal force. So on the left-hand side of the equation, we have a capital N for the normal force. On the right-hand side of the equation, we have a capital N for the units. So maybe you just want to leave the units out so you don't confuse yourself. Now that I know what the normal force is, I can find the force of kinetic friction. So the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. The coefficient of kinetic friction is 0.3, and the normal force is 169.9, and that gives us 50.9 newtons for the force of kinetic friction. So let's go ahead, and we're looking for tension, so let's bring the force of kinetic friction over to the other side so it would be positive on the other side. And we can put in the mass, which is 20, and g, which is 9.81, and the sine of 30 degrees. And then we have plus 20 times the acceleration in the x direction. I'm going to take the force of kinetic friction and put that in. And 20 times 9.81 times the sine of 30 degrees is 98. Maybe I should call it 98.1 since I have three significant figures there. And plus 20 times the acceleration in the x direction. Okay, now we've done everything that we can do using Newton's second law. We looked in the x direction, we looked in the y direction, but I still have an unknown in my equation here. But I haven't used all the information that they gave me in the problem because they told me that the initial velocity was 0 and the crate moves 6 meters in 3 seconds. So now it's time to look at what we can do with that information. So I need the acceleration. I have the change in time and the change in position and the initial velocity. So if I look back on my equation sheet, if I use equation 12.5, then I can find the acceleration. And this equation here, well, the object is just moving in one dimension, so I guess we don't really have to worry about that too much. It's moving in one dimension, so this would be in the x direction. That would give me the acceleration in the x direction because we already said the acceleration in the y direction is 0, so that should make sense. So the position of the object after it moves 3 seconds is 6 meters. Let me write out the equation first. So I have s is equal to s naught plus v naught times t plus 1/2 times the constant acceleration, so that's good, that's the constant acceleration, times t squared. So s is equal to 6 when s naught is equal to 0, v naught is equal to 0, so this whole term becomes 0, plus 1/2 times the acceleration, which I'm looking for, times the change in time squared. So 3 squared is equal to 9. And I'm solving for the acceleration, so I can multiply both sides by 2. That gives me 12, and then divide by 9, and that gives me 1.333 meters per second squared, and this is the acceleration in the x direction. So now I can go back to my equation for the tension and plug that in. So I have 50.9 plus 98.1 plus 20 times 1.333, and that gives me for the tension 175.66666. Let's round that to 175.7, and the SI units for force are newtons. So the tension is 175.7 newtons, and that concludes fundamental problem 1.